In this video, we'll do an example of very short proof, and then we'll have several more definitions regarding circles. So from the previous page, the previous video, we're going to prove the following. Prove the perpendicular bisector of a chord passes through the center of the circle. So draw a circle with center O and chord AB. Okay, then maybe I didn't even have to draw the center yet, but it's there, so we'll just go ahead and use it. Well, we know that OB is equal to OA. I'll even draw those two. OA, OB have the same length, and we know why, because they are radiuses of the same circle. Thus, O is equidistant from A and B. It has the same distance from O to A as O to B. Therefore, by the perpendicular bisector theorem, O lies on the perpendicular bisector of AB. Remember, if you take the collection of points that are equidistant from A and B, for example, O, or even way out here, you get the perpendicular bisector of that line segment AB. We've seen that already. So that was a very simple proof. All right, let's talk a little more about arcs. Given a circle C with center O. All right, let's see what we can say. A minor arc is the intersection of the circle C with its central angle and its interior. The interior of that central angle. And we'll do a picture of one down here. Actually, let's go ahead and do it. A minor arc. So I've got A, C, and B in order on the circle somewhere. And then I'm going to draw the angle AOB. All right, so the minor arc, and here's the fact about the minor arc. The measure of that minor arc, this is like a little arc over ACB. Usually it's written ACB, maybe like that, a little arc over it, but this is more like a, two straight lines, a hat. The measure is equal to whatever this angle is, the measure of that angle AOB. Now notice when we see ACB and we want the arc, we have to go from A, then to C, then to B. We wouldn't go the other direction where we'd go A and then we'd hit B and then C. We're talking about this arc right here. So that arc that I've shaded here, the measure of that arc is the same number of degrees as the measure of this angle right here. Now let's look at a semicircle. A semicircle is the intersection of C, the circle, with a closed half plane whose edge passes through the origin. So I'm just going to connect the line going through the origin like that. And we'll say that A and B is where it intersects. All right, so if C is on this side, it's not over here. So the arc we're talking about is this. This is the semicircle. So a semicircle is an arc. It basically is half of the circle. And remember, ACB goes from A to C to B. It doesn't go around the other direction. So the measure of the arc of a semicircle is 180 degrees because this angle, the straight angle, would be 180 degrees. All right, the next one is a major arc. Well, we had a minor arc before. Now we're doing a major arc. It's the intersection of the circle C with its central angle and its exterior. Not the interior of the angle, but it's the exterior. So we'll have one right here. And let's make the angle, make the ray OA and the ray OB. So we have an angle, but we're not talking about this angle right here. We're talking about this angle all the way around. It's called a major arc. It's greater than 90 degrees. So let me shade it in and notice how it's written, ACB. So we're not going to go A to B. We're going to go all the way around from A, cross through C, and then up to B. It's a major arc because it's more than 180 degrees. It's not this arc, it's this big arc right here. That's called a major arc. And how many degrees is that? Well, it's simply 360 degrees, which would be the complete circle, minus whatever this angle is, AOB. 360 minus the small angle, or you could say minus the measure of the minor arc, this arc right here. Okay, so actually we've already, kind of the title of this was, if A and B are the arc endpoints, and C is another point on the arc, then the measure of the arc, ACB, is what we just did down here.